All right, analysis 1B. Welcome to the new semester. Mr. Schwartz and I are super excited. I know it's not ideal that we're doing this online, but we've put a lot of work in, and we hope that you get a lot out of this semester. This is my first video, and concurrently, you'll be seeing Mr. Schwartz's first video too. My video is going to be on a volume, which is a topic that I believe that you guys looked at last semester with Mr. Rose. But we're going to look at it again because Mr. Rose told us that he kind of just did it at the end really quick, and maybe he didn't do the best job, is what he said. So let's go ahead and look at volume. So by the end of this video, we will have done a volume problem. In two different ways. And those two different ways are by the washer method and the shell method. I'm going to do my best to justify why these methods work for finding the volume of some sort of curve, some sort of a area that has been revolved around an axis. But if you want to look at this content in the textbook, which is on Canvas, it is in section 7.2 and 7.3 in the Larson text that you guys used last semester, but we're also going to be using that same text this semester. Alrighty then, let's go ahead and get started. Let's go ahead and justify the washer method. The washer method. All right, so let me give myself a coordinate plane and an arbitrary curve. Boom, right there. And what I want to do is I want to take the region, and let me go ahead and we're going to start here. Call this A. Over here, call this B. We're going to take the region from A to B that the curve here makes with the x-axis, this region, going to call it R, and we are going to revolve this around the x-axis to figure out what the volume of that solid is going to be. Let's look at just one section of this region. Let's look at this section right here. All right, this is a very small amount of the thing. We're going to look at this as this rectangle gets smaller and smaller. So let's look at the dimensions of this thing. All right, we're going to go ahead and say this is dx. This is the thing that we're going to be making smaller and smaller. All right, the height of this is the output of x in the function. So let me go ahead and give this thing a name. This is f of x. The height of this thing is f of x. If I were to then revolve this around the x-axis, I would get a disk. Let me do the best job I can in drawing that. So it's going to be down here. Now we have this disk here. What is the volume of this disk? Well, it is a cylinder with height delta x and radius f of x. So let me go ahead and do that. We have height delta x, we have radius f of x. And what's the formula for a cylinder? That's going to be, volume is equal to pi r squared h, the area of the circular cross-section times the height. Which means this cylinder over here is going to, so I'm going to call it cylinder I, right, because we're going to have lots of these cylinders. This cylinder over here has a volume of pi. Well, the radius is f of x, as we have said. We're going to go ahead and square that thing. And the height is delta x. And what we want to do next is sum up all of the cylinders here, and then we'll get an approximated area for the volume of this curve being revolved around the x-axis. So what we're going to do, the volume of this revolution, I'm going to go ahead and do that in white. Now the volume of this revolution, an approximate, is going to be from I to n, we have pi f of x quantity squared delta x. And then if we take the limit as delta x gets closer and closer to 0, that's when this thing becomes our integral, and that's going to be from a to b pi f of x squared dx. And that pi can get popped out just because it's a constant. All right, so I know that at the top of this page it says the washer method. But that was kind of the disk method. I mean, the shape that we made there, the solid that we made there, is a disk. Right? The washer method is just, what if there's a hole in the middle? What if we're revolving around something where the region is not touching? So let me go ahead and just put over here disk. This is the disk method. But in general, we're looking at the washer method. So let me give myself another region. Right here. Cool. F of x. I'm going to give myself a second curve right here. I'm going to call it g of x. Right? Because what I want to do is I want to revolve f of x around the x-axis, but I also want to revolve g of x around the x-axis and take that out. Right? This is going to give us what we call a washer. If you've ever been like, well, you guys all took Mr. Street's class, I'm sure you spent a lot of time with washers. Let me go ahead and draw what I mean. So about right there, that's good. Awesome. So there's my disk. If I were to revolve f of x around the x-axis. Now I'm going to revolve g of x around the x-axis, and I'm going to be left with a washer. This right here. That right there. Cool. And not the best drawing, but a drawing nonetheless. All right, I have this green disk with this red disk removed, making a washer. I think what might help is if I give it a little bit of a 3D dot. Cool. So what is the area of this washer? Well, we have that formula for a cylinder is pi r squared. So we have pi f of x squared. All right, and let's go ahead and do this from a to b. Dx. All right, and we are going to be subtracting out this red amount. So from a to b, pi g of x squared dx. But what's nice is I can turn this into one integral. I can go ahead and say that this is going to be from a to b of pi f of x squared minus g of x squared dx. All right, so this is the washer method. All right, if we are revolving two curves around to create some sort of, I'd imagine if this were to get revolved around, it'd be a pretty thick vase looking thing. But we are removing some space in the middle. This is the washer method. And this is going to be that formula to find the volume. So let's go ahead and use it. And I have a really annoyingly hard problem that makes things much more complicated, but that'll address those complications. So I want to look at the following two curves and the region defined by them. X equals y squared and x equals 2 minus y. All right, so let's draw these things. Right. Oh, and I want to revolve this about the line y equals 1. That's important. That makes this a problem. Okay, so x equals y squared. Let's go ahead and draw that. All right, this is going to be a parabola that's been rotated 90 degrees clockwise. All right, let me go ahead and sketch this curve. It's always kind of hard to do it sideways on the computer, because in real life you can just turn the page sideways. All right, that will do. Not the best, but will work. And then we also have the curve. Let me go ahead and change the color. We have 2 minus y. X equals 2 minus y. So that is going to be, let me go ahead and move this around actually. I'm going to subtract, oh, that's nice. Y equals 2 minus x. Right, so intercept at 2 and slope at -1. So boom, boom. Oh, and look at that. It intersects perfectly, right? I am not going to. But if I needed to find out when these two curves intersected, I would just set them equal. But in this case, I'm given when they're equal because they intersect at grid lines. Right, we have negative 1, 1, and we have down here 4, -2. Cool. We want to revolve this region around the line y equals 1. So what we need to, I'm realizing I'm saying cool a lot, and I apologize. We need to look at the rectangles that will rotate around this line, revolve around this line, and create washers. So let's just go ahead and draw one right here. All right, and let's establish its dimensions. So we have delta x here. All right, this is going to be integral dx, not dy. And this height here, well, what is this length right here? This length is 1, let's go ahead and call it large r, 1 minus this curve right here is negative square root of x, right? If I mess around with this, I'm going to get y equals plus or minus the square root of x. So down here, let me actually add it to my picture. This is f of x is equal to negative square root of x. And up here we have let's call this f2. f1 of x up here is positive square root of x, all right, if we turn this into a function of x rather than y. Cool. So this large radius is 1 minus the negative square root of x. Right? This small radius right here is 1 minus this blue line, which is 2 minus x. So 1 minus 2 minus x. Let's call that tiny r. So this ends up being 1 minus 2 minus x. That's going to be negative 1 plus x. And down here we have 1 minus negative square root of x. That's going to be 1 plus the square root of x. Cool. So we can now almost do this integral because if you notice, if we move along and we make rectangles, we make more rectangles. Once we get to 1, 1, once we get to the x coordinate of 1, we actually switch what defines the dimensions for the rectangles. All right, everything to the right of 1, x equals 1, is going to have the dimensions large radius 1 plus root x, small radius negative 1 plus x, and what is that? The height of our washer is delta x, but over here, the height is still going to be delta x, but our small radius is actually now going to be 1 minus positive square root of x. Remember this white curve right here? Positive square root of x. And the large radius, we add a little dotted line, that's going to be 1 minus negative square root of x, or 1 plus root x. Right? So the dimensions to the left of 1 and to the right of 1 of our washers are going to differ. So with that said, there are going to be 2 integrals here. All right, let's go ahead and write those integrals down. Let's choose purple. I haven't been using purple enough. Okay, so we have the integral from 0 to 1, right, the volume of this thing. It's going to be the integral from 0 to 1 of pi, I could throw that pi in the front if I wanted to, but I choose not to, r, which in this washer's case is going to be 1 plus root x minus 1 minus root x. Right? That's our radius, but we need to square these things. And then our height is delta x, and in an integral, that's going to be dx. Right? This is only from 0 to 1. We also need to add from 1 to 4. We have 1 plus root x squared minus negative 1 plus x squared dx. Awesome. And then when we evaluate this, we will get the volume of this red region revolved around the line y equals 1. Let's go ahead and do it. All right, I've gone ahead and I've added it to the next page already, and this is actually where I suggest that you pause the video, do this integral, and then fast forward so you don't have to listen to me make mistakes and also waste your time. So go ahead and do this by yourself, and then just fast forward to the end. And if you do struggle along the way, you can always just play my solution back, because this is about to be a little bit nasty. So we got 0 to 1. I'm going to expand this, so that's going to be 1 plus 2 root x. 2 root x plus x minus 1 minus 2 root x plus x. Well, so some things are going to cancel. That's pleasant. Dx plus 1 to 4. We're going to have 1 plus 2 root x plus x minus, what do we got? We got 1 minus 2x plus x squared. Yep, that should be correct. And then let's go ahead and continue. So 1 minus 1, that's 0. 2 root x minus negative 2 root x, that's 4 root x. And then x minus x, that is 0. So that is that. That is nice. Let's hope that the other one follows suit. Over here we have 1 minus 1. That's good. We have 2 root x minus 2x, so that's not going to cancel. Oh, but it's plus 2x, negative 2x. So it's plus 2x, and then we have x minus x squared. So that is simply going to be an x minus an x squared. And it looks like we're going to have 3x. So I'm actually going to go ahead and write that. Okay, so let's integrate this thing. I'm actually going to write this as a 1/2 because that's more pleasant on my eyes. So that 1/2 goes to become a 3/2. We divide by 1/2, which is the same as multiplying by 2. And we are evaluating, so I'm going to go ahead and write 0 to 1. Awesome. And then over here, we are going to have, we're evaluating from 1 to 4 of a bunch of stuff. So that, once again, is going to be, I'm going to make that a 1/2. Ooh, I think I messed something up here. We're not dividing by 3/2. We are dividing by 3/2, not 1/2. So there should be a 3 down here. Cool. Sorry about that for the people that were screaming in your home. This is going to be a 3/2, so we're going to divide by 3/2, which means it's going to be 4/3 x to the 3/2. This is going to be a 3/2 x squared, and this is going to be an x cubed divided by 3. Believe I didn't make any mistakes there. Let's go ahead and evaluate. So plug in a 1, we get 8/3. Plug in a 0, we get 0. So we're going to have pi times 8/3 minus 0. I'm just adding that so we remember that step. Maybe it's been a whole summer since you did calculus. Hopefully you did. Hopefully you did the summer math packet. And over here we're going to have 4. This is going to get kind of nasty, but 4 cubed is 64. Square that is 8. So we're going to have 8 times 4, 32/3. Over here we're going to have 16 divided by 2, which is 8 times 3, which is 24. And then here we're going to have 64 divided by 3. That's just 64 divided by 3. Let's plug in 1. We're going to get 4/3. We're going to get 3/2. And we're going to get 1/3. Let's see what this all comes out to. Let me not forget my pi out here. Okay, I have brought that last page over, and we have 8 pi over 3. Then over here we have 32/3 plus 24 minus 64/3. Let's go ahead and write this thing as thirds. So multiply by 3 over 3. That's going to be 72/3. 72/3 minus 64/3, that is 8/3. And 32/3 plus 8/3 is 40/3. And then over here we have 4/3 plus 3/3 minus 1/3, so that's 4. 4/3 minus 1/3, that's 3/3, that's 1. Plus 3/2, which ends up being, let's see, 2 halves plus 3/2 is 5/2. All right, so we got 8 pi over 3. And then over here we have 40/3 minus 5/2. Let's go ahead and write that as 86ths and 15/6. So we're going to have 65 pi over 6. Sweet. So we got 8 pi over 3 plus 65 pi over 6. Common denominator, let's make that a 6. Let's make that a 16 pi. And then 65 pi plus 16 pi, that's 81 pi over 6. And 3 goes into both of these. 3 goes into 81 27 times. 3 goes into 6 2 times. There is our answer. I guess you should write units cubed or something because it's volume. All right, I did not enjoy doing that integral at all, but it worked. 27 pi over 2, and that is the correct answer. This was nasty. We had to break it up into 2 integrals. All right, hopefully there's a better way. But the washer method in a nutshell is you are taking some sort of cross-section, revolving it around an axis that's making a washer, and what is the volume of that washer? It's that, that formula r squared minus the smaller of the 2 radius squared. All right, let's move on to the next method. All right, that last method was terrible. So I want to introduce to you, well, don't get me wrong, that method that we just talked about is effective in many situations, but there is an alternative way to find the volume of revolution using something called the shell method. So let's talk about that. All right. So let's say I want to revolve this curve around the x-axis. And I'm actually going to get rid of x here because f might be a function of y, as we'll see actually in my example. But I want to revolve this curve and the region made by this horizontal line and this vertical line. Right? I want to revolve this region around the x-axis. I'm actually going to go ahead and get rid of those dashes in there so that I can draw in that space and it not be too busy. So the idea with the shell method is I'm going to take a little bit of this region right here, and I'm going to revolve it around the x-axis, and I'm going to immediately have a cylinder with an inner cylinder cut out. And then I'm going to do the same thing with as many, let's call them cylinders with holes in them. I'm going to do as many of those as necessary to cover this entire region. So I'm going to go ahead and get rid of that extra rectangle that I drew because I want to find the volume of this rectangle revolved around the x-axis. All right, so what are the rectangle's dimensions here? We have delta, in this case delta y, Right, that's the thing that's going to be varying. Let's just go ahead and call this length the height. Right, and then we're revolving this around the x-axis, so we're going to have two radii, like we did in the washer method. We're going to have this height and the smaller one. Let me just do some dotted lines so we know what those ones are talking about. A little bit off, my bad. Let's go ahead and call this big R and this little r. So the question is, what is the volume of this shell that we're making? Let me just draw the shell real quick. All right, so it's this cylinder with a cylinder removed. So the total volume without the cylinder removed is going to be pi big R squared h, and the small one that we're removing is going to be pi little r squared h. So the volume of this shell is pi r squared h minus pi little r squared h. All right, so it's looking very similar to the washer method, but we have this shell now. Right? The trick to this method is to recognize that we can relate these two radii by looking at the average radius of this rectangle. Right? Let's go ahead and call the average of this p. Right? And let's go ahead and just recognize that delta y is the width of this rectangle. Right? R is going to be p plus the width divided by 2, and little r is going to be p minus the width divided by 2. So I'm going to go ahead and I'm going to substitute them into this equation. So we got pi, p plus width divided by 2 squared times h minus pi, p minus width divided by 2 squared h. All right, while I'm at it, let's go ahead and, no, that's what I want. Cool. Let's simplify this thing. So I'm going to factor out a pi and an h, and I'm going to be left with p plus w squared, average height, the average radius, plus the width divided by 2, minus the average radius, minus the width divided by 2. And then just a little bit more simplification. Let me go ahead down here. We are going to have pi h. It's going to get a little bit hairy. We're going to have pi squared. We're going to have 2 times p times w over 2, which is just pw. And then we're going to have w squared divided by 4. And then on the other end, we're going to have, let me go ahead and put parentheses around those, minus, once again, p squared. This time, minus pw. And then, once again, plus w squared divided by 4. And then things are going to cancel. P squared minus p squared, 0. W squared over 4 minus w squared over 4, gone. But pw minus negative pw is 2pw. So our final formula, 2. This ends up being 2pw. 2 pi pw h. Right? The volume of this rectangle revolved around the x-axis is 2 times pi times the average height times the width, ends up being delta y for us. This is the thing that's going to vary. This is the thing that we're going to take the limit as delta y goes to 0. And then the height just is whatever it is. It's going to be based on whatever this function is. So if we take the limit as delta y goes to 0 of 2 pi pw delta y h, we get that nice formula. All right. We're going to, what is it going to be? 2 pi p h dy. All right, 2 and pi are both constants. The reason why I kept p and h in here is because p is going to vary depending on which rectangle you're looking at, as is h. All right, as you draw new rectangles, the h will change and the average height will change. All right, with that said, let's do the previous example that we did, but with this formula instead. So we want to take the two curves x equals y squared and x equals 2 minus y, and we want to revolve around or about the line y equals 1. All right, let's go ahead and get those curves. All right, we had them before. It's always difficult to draw sideways on the computer, so give me a second here. There we go. Cool. All right, that is our x equals y squared. Right, this is going to be a function of y. Right, and then let's go ahead and draw 2 minus y. So there. Boom, 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 boom. Oh, so our intersection points are easy to tell, as they were. All right, here is our region that we want to revolve, and we're revolving it around the line y equals 1. Let me go ahead and label this thing right here, 2 minus y. Cool. All right, let's go ahead and draw our rectangle so we can figure out all the information that we need. All right, so what is the height here? All right, the height is, it's going to be a function of y, and it's going to be 2 minus y minus y squared. Right, that's our height, because this is 2 minus y, we're subtracting y squared. And then our we have our delta y right here. This is going to be an integral with dy. And then what is our average radius? What is the p-value? P of y is going to be 1 minus whatever the y value is at whatever point. So the y value here looks like it's about negative, but whatever. It is whatever the y value is. So 1 minus y. All right, and as established, the volume of this shell is going to be 2 pi times p of y, which in this case is 1 minus y, and h of y is 2 minus y squared. Dy from, where are we coming from? We're going from negative 2. All right, don't forget we're talking about y here. Y equals negative 2 to looks like 1, right? I could set these equal to establish that it's negative 2 to 1, but in this problem we can visually see that it's negative 2 to 1. Cool. So let's go ahead and solve this thing. This looks pretty simple to solve. We can pull that 2 pi out. And then what do we got? We got 1 times 2, which is 2. We have 1 times negative y, which is negative y. We have 1 times negative y squared, which is negative y squared. Then we have negative y times 2, which is negative 2y. We have negative y times negative y, which is positive y squared. Looks like those, not that. Those are going away. And then we have negative y times negative y squared, y cubed. Let me not forget my dy. All right, the volume is going to be from negative 2 to 1, we have 2 minus, it looks like 3y. Yep. And we have plus y cubed. Cool. dy. All right, I'm starting to run out of room. So I'm going to grab this and take it to the next page and finish this thing. All right, so we have, what was it? It was until 1. That got clipped. We got 2 pi, and then let's integrate this thing. Definite integral from -2 to 1. Let's keep that 2 pi outside of this thing. We got 2y. Then we have y squared. We're going to have 3 halves y squared. Let me not forget that. And then we have y cubed, so that's going to be y to the 4th divided by 4. So just basic integration techniques. And then we evaluate. So we have 2 pi times, let's plug 1 into everything. We get a 2. We get a 3 halves. And we get a 1/4. And then we're subtracting. We get a, ooh, this is a little bit more complicated. We get -4. We get y squared, which is 4, times 3, which is 12, divided by 2, which is 6, and it is -6. And then we're going to get, plug 2 in, 2, 4, 8, 16, divided by 4, which is +4. Wonderful, the 4's cancel. We get a minus 6, it's a +6. Over here, we have 2 minus 3 halves, it's 1/2. 1/2 plus 1/4 is 3/4. All right, sorry, I'm just jabbering about arithmetic. I apologize. And this is going to be, I want this to be fourths, so I'm going to multiply this by 4 over 4. 6 times 4 is 24, so 24 fourths. 3 fourths plus 24 fourths is 27 fourths. 2 pi times 27 fourths. Boom, boom. We are left with 27 pi over 2, which is what we got on the previous attempt, the much more nasty attempt. All right, and here we are back at the first page. Just wanted to remind you guys what we did. We looked at volume problems, and we did them in 2 different ways. We used the washer or the disk method, and we also did the shell method. And in the problem that I gave you, the shell method was better, but let me remind you that sometimes the washer method will be better. But sometimes the shell method's better. So you just have to kind of know which one is better, and that comes with practice, which we will do on Thursday and Friday, depending on when you have Mr. Schwartz or I. So go ahead and wrap this one up. I recommend reading 7.2 and 7.3 to just get another perspective. But with that said, this is the end.